So, main objective for this week is going to be covering one last chapter. It's going to be chapter 10 on vibrations, waves, and sound. At the end of this week and into one lecture next week, we're going to move into exam review territory. I'm going to post another practice exam like I did for the practice test and an answer key for it. We'll let it go over everything you need to know to succeed on the test, on the exam, and then we're heading towards the end. How y'all feeling? Any questions, concerns, etc. before we get started with our last chapter today? Do you permit it? One last thing, if you haven't picked up your test yet, please feel free to do so. It is your test, it's your copy. You are allowed to and encouraged to keep it. So, Chapter 10. And for your last one, possibly more concept-driven than the others, just because I want to make sure that the concepts related to waves and sound are the ones that stick with you, and try to go over all the things that I think are most important to how humans perceive waves. But before we do that, the first thing we're actually going to do within this chapter is go over some vocab words, basically all the terms we're going to be using to define and describe and measure waves and wave-type motion. So, first off, those vocab words. The first term we're going to go over is actually kind of at the core of the entire chapter, and that's going to be simple harmonic motion. This term refers to a state where an object or a material is undergoing repeated simple motion back and forth between 2 points, usually driven by some sort of a restoring force. As an example of simple harmonic motion, I currently have at the front of the room a spring with a mass hung from it. Note that this is the configuration that the object wants to be in. This is currently the object's equilibrium state. And if I upset this balance by physically pulling down on the mass and let it go, it begins moving back and forth between 2 fixed points, between a certain low point and a certain high point. And it'll constantly accelerate and move between those 2 positions. This is simple harmonic motion. It's simple motion in that it's just motion up and forth, back and down in the one axis. And it's harmonic motion in that it's doing the same thing over and over again repeatedly at a constant frequency. So simple harmonic motion refers primarily to this and this sort of motion. And technically, all the things we talk about this week are going to be forms of simple harmonic motion, even the waves that we're eventually going to move on to. Because as it turns out, this is basically a wave, and this physical apparatus formed the foundation of how humans began to study and describe waves. So we're going to go through all these vocab words, talk about how they refer to waves, but also talk about how they refer to this and how this went on to inform human understanding of waves. I'm also going to use the word oscillation a lot this week. Oscillation is functionally a synonym to simple harmonic motion, the way that I use it. If something is oscillating, it's moving back and forth between 2 points over and over again, which is simple harmonic motion. That object is currently undergoing an oscillation for simple harmonic motion. Pendulums do this as well, and later on this week we will sort of do some math for that and for pendulums. I don't have a good pendulum, so I'm just using a power cord right now. This is also simple harmonic motion because the plug is just moving back and forth repeatedly between 2 fixed points. So technically, this is a wave too, in a way. So, simple harmonic motion is the action that these objects and these waves are undergoing. And now let's look at the things that we measure about waves in simple harmonic motion. First of which is going to be amplitude. On the board, I have drawn what most people tend to think of as a wave shape. Does that sound about right? This is very specifically a sinusoidal wave function, which means of or referring to sine, the literal sine button on your calculator. If you've ever graphed sine x in the graph function of your calculator, it spits out something that looks like this, either sine x or cosine x. So this is literally sine and cosine graphed over time, and it creates a pattern like this. It turns out, even in the chapters where we aren't doing trigonometry, you still are not free from sine and cosine. So this is what we often think of as a waveform, and I'm going to compare this to what's happening for the spring right now. First, from the definition of amplitude. The amplitude of a wave or of simple harmonic motion refers to the distance, physical distance measurement between the base state and maximum deformation. What that means is, right now, I've reset this so that it's not moving. This is currently in its base state. Nothing is happening. And if I deform the spring, by this distance from here to here, and let it go, the mass is now going to begin oscillating between two fixed points centered on the base state. The amplitude is the distance from base to either extreme. It is not the distance from top to bottom, it's from base to either top or bottom. Same is true for this waveform. I'm going to try to describe this like you're looking at the ocean. If there aren't any waves, the still water would sit at this height, the dotted line. And then once the waves start pouring in, they will rise up to a certain point. This is called a crest. And they will also dip to a certain point. This is called a trough. This point is not the still water. The dotted line is the still water. If you've ever been bobbed around by waves in the ocean, you've probably noticed they take you up and then they take you down. That lowest point is lower than what the still water would be. And the amplitude of the waves is the distance from the normal still water up to the highest point or down to the lowest point. It is not from here to here. It's from base to either extreme. Just want to make that clear. Wave amplitude is basically just the size of the wave. It is a physical size measurement, so you can measure it in meters. There's no new unit for it. It's just a specific length measurement. And to try to compare this to the waves you experience, amplitude of an ocean wave would be its physical height. The amplitude of a sound wave would be most comparable to the volume of the sound, because the physically more intense the wave is, the bigger the oscillation for the sound is, the more energy it's pouring into your ear, and the more it hurts. There is another way to physically measure the size of waves, and rather than measuring their height, we are going to measure their length. So wavelength is next. The term wavelength literally refers to the physical length of a wave. The symbol for that, the variable in your formulas, is going to be lowercase lambda. I keep confusing myself as to whether this is lambda or gamma. But if it's lambda, lowercase just kind of looks like a rotated y. The way I write it, it is basically a mirrored rotated y. And this represents, again, physical length, like literal tape measure length of an entire waveform. I'm actually going to generate a wave right now on this apparatus I have at the front here. This one. This is a standing wave, and this is a one full wavelength. The definition of one wavelength, the length of one entire wave, is the distance that the wave travels as it goes through one complete cycle of its oscillation. Any wave, it always is going to start from a rest state, from the base state. Then it will go to one of its two extremes, cycle back down, then go to the other extreme, and then cycle back to rest. So this, from here to here, is one full wavelength. That is one full cycle of the entire wave. And the wavelength is the physical length of the wave between those 2 points, between here to here. Alternatively though, as long as you are measuring one full cycle, you can start measuring from anywhere. Say you start from here at one of the crests, you would measure the distance from here to the next crest. As long as whatever point you start at, you measure physically to the next iteration of that point. Here, you go from crest down up to the next crest. If you start here, you'd measure up to the next rising edge. You can measure from trough to trough if you wanted to. Here, I know it might kind of look like these are two different troughs, but if you freeze time, note that one would be up and one would be down. And so this is one full wave, this is one full wave, and it's just cycling back and forth between those extremes. Oh no, I upset it. There we go. So this is one full wavelength, one full cycle, and that length it's literally the physical length from end to end of one entire wave. Since its length, it's once again still measured in meters. Questions so far about these two wave measurements? All right. Now, the next variable does involve a new unit, but it's a unit and a concept that you, I hope, have at least heard of before. Next is wave frequency. Frequency of a wave tells you how many waves pass every second, how many events occur in 1 second. It's literally a measurement of how frequently something happens, how often it occurs per unit of time. Frequency, and this actually applies to more than just waves. Number of events per second. In the case of this object undergoing simple harmonic motion, if I took a stopwatch and I timed out 1 second, the frequency would be how many full oscillations this thing goes through within that 1 second. So if I count out how many times it goes from bottom to top to bottom again within 1 second of time. If something has a frequency of 1 event per second, then it happened 1 time in 1 second. 2 events per second is 2 times in 1 second. And this has its own unique unit, 1/1 second, which is the same as 1 hertz, the same unit of hertz that you might measure sound pitch in. So a sound's frequency determines its pitch, and different frequencies of sound wave, what the frequency of the wave means is how many of those single waves pass through or hit your eardrum every second. If a wave has a frequency of 1 hertz, that means that 1 full wave will pass you every single second. 2 hertz, 2 full waves pass you every second. Most common humans, the sounds that most humans tend to interact with on a daily basis, like human speaking voices, sometimes center around 5,000 hertz. And so if you are hearing 5,000 hertz sound wave, that means that every single second there is 5,000 waves traveling into your ear. So frequency is how frequently something occurs, number of events per second, measured in units of hertz. Questions about that? You guys have dealt with at least the term hertz before? All right. Last vocab word before we move on to using these vocab words is period. And this is literally the inverse of frequency. Period of oscillation asks you, how long does it take for something to go through 1 full oscillation cycle? instead of events per second, it's number of seconds per event. Period of oscillation, it's a period of time. The time it takes to go through one full cycle of something. That means it's literally just a time measurement. And that's why the variable for it is uppercase T. Lowercase t is general time, uppercase T is specifically how long does it take this thing to happen one time. In the case of this pendulum, this spring, the period of oscillation would be the time it takes to go from here back down. So the time of one full cycle. And since this is seconds per event, it is measured in units of seconds. And it is literally the inverse of frequency. Its frequency is seconds per event, and period is events per second. Sorry, I got that backwards. Frequency is events per second, period is seconds per event, sorry. They're literal inverses. If you have one, you can flip it over and get the other. Compare back to sound real quick. If you're hearing 5,000 hertz sound, that means that every 1 second, 5,000 waves enter your eardrum. And the inverse of that is for period, if you take the 5,000 and flip it, the period for those waves is 1/5000th of a second. One wave travels and hits you every 1/5000th of a second, if that is the frequency of the wave. Any questions about these vocab words before we start applying them to some things? All right. I'll just mention again, we're going to be talking about waves and various forms of simple harmonic motion this week. Amplitude, as it relates to sound, would affect volume. Again, the bigger the wave, the more intense it is, the louder it is. And frequency correlates to what pitch of sound you are hearing. So, high pitch, low pitch, high frequency, low frequency. Now, why do we care about any of this? Why do we specifically care about how this relates to that spring over there? I mentioned that human understanding of waves originated with things like that. And in fact, we used to draw sine waves using a mass on a spring. Physically, if you take that, stick a pencil on the object and have it scroll up and down across a sheet of paper, and you have that paper scroll sideways so that it's moving with time and the pencil's moving up and down against it, it draws out this. And so actually, I think some lie detectors or EKGs used to literally be a pencil on a spring drawing across scrolling paper. That is basically a wave. Like, that draws out this motion. And so again, a lot of our understanding of waves came from this sort of thing. And what that means for waves is, what we're going to want to take from this is that waves are comprised of traveling energy. We've talked about the energy interaction in that spring before. We've done a lab and a few in-class examples that involves a spring causing an object to move up and down. To briefly review, this object normally in its base equilibrium state wants to hang out here. And if I then pull down on this mass, I have added EPE into the system. When I release this mass, that EPE is going to start transforming into a bunch of different states. It's going to become KE when the mass is moving. It's going to become GPE when the mass is at its highest point. The EPE level of the spring is going to fluctuate in opposition to those two forms of energy. And so we've looked at how the energy in this system is constantly transforming. But it's also traveling, because literally it's going to be switching which object possesses it. At times the mass has it in the form of KE or GPE, and at other times the spring has it in the form of EPE, and even in a little bit of KE as its coils are moving. So the energy here is not only transforming, it is constantly transferring and traveling. The energy in that spring travels between its two ends, between the mass and the spring. And the same is true of every single type of wave. Every wave you can think of is just traveling energy. That includes sound, includes light, includes ocean waves, includes earthquakes. I want to briefly turn your attention to this apparatus on the desk. Note that this is the machine you're going to be using for lab this week. You've got, I'll talk about the parts here. This thing is just a speaker ripped out of a sound system, literally. And all those speakers are, it's literally just something like a film shaking up and down repeatedly. This is just an actuator pushing up and down on the film of this drum here, basically. And it just makes sound of a certain frequency based on the frequency it's shaking at. And right now I can control that frequency using this dial. And in lab you're going to have the same thing. A dial controlling the frequency of this speaker, and a string will be tied to that speaker so that the string starts shaking at the same frequency. This is specifically called a standing wave because it's kind of like the wave is standing still. It's, on the desk, standing in one place so that we can watch it, as opposed to sound waves which just shoot off and never come back usually. So when I say standing wave, I'm referring to this. You're going to make standing waves in lab using this speaker system. And what this thing is doing is the speaker drum itself is oscillating. That's going to put energy into the rope. And the energy is what's going to travel from one end of the rope to the other as the wave travels from one end to the other. And the way that standing waves work is that energy is going to strike the other end and then bounce back as an echo. Oh no, my calculations were off. That'll do. The energy bounces back as an echo, and it's constantly just looping back and forth between the 2 points, and that's why the waveform remains. It's why you can see it doesn't lose energy over time. It's just going back and forth, and this is constantly supplying more energy so that it doesn't peter out because of friction. If I turn it off, it just peters out. And once again, this thing is just putting energy into the rope, and that energy is what's traveling from one side to the other. I'm going to turn it off. Let's try to help demonstrate this point. So here's our base state equilibrium for this elastic cable. And I'm going to, instead of letting the speaker do it, I'm going to pluck it with my hand. So I'm just going to grab part of the rope and pull it up. Since the rope is elastic, I've deformed it, I have given it elastic potential energy, so I have added energy into the system, and once I let go of it, once I strum it, that energy is going to travel back and forth along the rope. But I want you to notice something specific here. I'm going to do it again. I'm going to grab this part of the rope, pull up on it, and note I'm grabbing just to your left, that is left, right? Just to your left of this knot. Actually, in fact, I'll even grab the knot directly. I'm grabbing hold of the knot, and I want you to note what happens to the knot as the wave travels, all right? Does the knot travel? No. The knot is going to undergo simple harmonic motion. It's going to vibrate back and forth between 2 points, but it doesn't actually travel down the length of the rope with the energy. The energy's traveling horizontally back and forth, zooming constantly, but that knot doesn't travel. It just oscillates in place. That is true of every type of wave. All waves are just traveling energy. The wave itself is just the traveling energy. And what you see, what you actually kind of experience, is the medium that the wave is traveling through undergoing simple harmonic motion while the energy moves through it. The wave itself is just traveling energy. That energy is going to travel through a physical medium, and the medium will usually vibrate, undergo simple harmonic motion as the energy travels through it, but the medium doesn't go with the wave. The wave is just the energy. The medium does not travel. And deep down, you may have observed this subconsciously. For example, sound waves. Humans experience sound as a vibration through air. So there's literally air in the room between us. When I speak, my throat vibrates and puts energy into the air. And that energy travels from my throat to your ear as a sound wave. The air is required for that sound to travel. The air is the physical medium that the sound travels through. If that air was not there, the sound would not travel, and that's why you cannot hear in space. If there's no air in space, that means that there's no medium for the sound waves to travel through. Here on Earth, we have the air, and when I speak, I am putting energy into the air, and that energy travels as a vibration through the air. But the air doesn't go with the energy. The air is going to vibrate once it has the energy. So, like, if I were just examining, like, we were looking at the sound wave from my throat to the wall, and we were examining this pocket of air right here. As the energy travels through this pocket of air, the air would vibrate the moment the energy's there, but then it stops and stays still once the energy's gone. The air doesn't go with it. If the air did go with it, I'd create a typhoon every time I talked, because all the air that the energy touches would go with it and rush towards you, and, you know, every time anyone spoke would just be a gale force hurricane. The medium doesn't go with the energy. The wave itself is just the traveling energy. This is true of every single type of wave. In ocean waves, the physical ocean will oscillate up and down as the wave travels through a specific spot, but not all of the water it touches is going to go towards the coast with it. Because waves start miles out, and they don't bring all the water up to the shoreline with it. What waves mostly do is they just kind of roil up the water that's already at the coast and crash it back down. They don't bring the entire ocean to the shore with them unless it's a tidal wave. That has its own unique physics. I'll point out again, this is even true of earthquakes, because an earthquake is technically just a wave traveling through the ground. The medium for earthquakes is the earth. And when an earthquake happens, say if a fault line slips, that puts energy into the ground. The ground is going to vibrate as the energy travels through it, but the ground stays in place. It doesn't, like, not every single rock travels with it, which is good, because then every fault line would just explode into a giant hole every earthquake, as all the earth just erupted outwards, traveled with the earthquake. So it's good that doesn't happen. Earthquakes are devastating enough as it is. So, the wave itself, all the waves we talk about this week, it's just referring to the traveling energy. Most waves require a physical medium, but the medium doesn't go with the wave. Good so far? All right. Now, what are we going to do with this information? Since waves are made of traveling energy, the energy is traveling, and that means it has a velocity. The waves have a velocity. This is the speed at which the energy is traveling from one place to another. It's not necessarily the speed that the object is vibrating at. It's the speed that the energy moves from point A to point B, from origin to reception. All waves have a speed because they're all traveling energy. And every different type of wave is going to have a different speed. You might be loosely familiar with this basic concept. For example, various physics classes you might have taken in various forms of media would probably mention the speed of sound. In physics, during standard scientific room temperature, room pressure scenarios, we consider the speed of sound to be 343 meters per second. That is, again, the speed the energy of the sound wave travels at, not the energy that the particles move at, because again, the air particles here don't go with the energy. But the energy is able to go very fast from point A to point B. And different types of waves will have different speeds. For example, in comparison to sound, you may have also heard the speed of light come up occasionally. And that speed is capped at 3 times 10 to the 8th meters per second. Fastest thing in the universe, about 1,000,000 times faster than sound. Well, not too dang fast. This is literally the speed limit of the universe. Nothing goes faster to our understanding. So different types of waves all have different speeds. They represent the rate at which the energy travels from point A to point B. And the way that you calculate wave speed is you take the frequency of a wave and multiply it by its wavelength. Those two things multiplied together tell you the speed of that wave. And this works because my computer just died. This works because frequency is measured in hertz, and 1 hertz is 1/2. Wavelength is measured in meters. So this formula multiplies meters by 1/seconds, and that gives you meters per second. So that's where this formula comes from. The distance a wave travels per, the time per wave. And you can do this with any wave as long as you know its frequency and its wavelength. Every different type of wave will have a different speed depending on the type of wave and what it's traveling through, and that goes on to inform how its wavelength and its frequency interact. We're now going to demonstrate this using the standing waves. Let's see what's next. Try to get my standard frequency back. We are now going to take this standing wave and measure its amplitude, wavelength, frequency, and calculate the velocity of the wave given all that information. Getting some practice for how you're going to be using this apparatus in lab this week. So we're just going to use this wave that I currently have up here. I will go ahead and show you. This wave is currently at 10.4 hertz, so the device is just going to tell us its frequency. Now we're going to go down the list, just demonstrating how to calculate and measure these other things. First up is wave amplitude. That is, again, the distance from the base configuration to either the tallest point or the lowest point from the base length. What's interesting, what I find nice about standing waves here is they have a certain number of points that basically don't go anywhere, and we call these nodes. And this wave actually has 3 nodes. You got one in the middle here, and then technically the points on either side. So this is a 3-node standing wave. Conversely, we've got 2 points here of maximum deformation. Those are antinodes. So we've got 3 nodes and 2 antinodes. And a 2 antinode wave like this is 1 full wavelength. Because we already talked about how 1 full wavelength is from rest, up, down, and back to rest. So this is 1 full wavelength. We're first going to measure its amplitude, which is, again, standing waves are nice because the nodes are at the default state. This is the base height. I'm going to turn it off real quick just to show. So note, this is where the node was. And this is the base configuration. Once I turn it back on, that spot didn't go anywhere. So these are great for helping you find amplitude. I'm going to note what height this spot is at, then note how that compares to the highest point. That is a displacement of about 35 millimeters. So that would be the amplitude of this particular wave. I need this one right away. So amplitude, 35 centimeters. Thank you, sorry. I have been getting my units wrong all day today. Please call me out on that. Now for wavelength. I mentioned again, this is one full wave because it's from rest up to down and back to normal. So this is one full wave. You want to look for 2 antinodes in that case. And that means that its wavelength is going to physically be the entire length of the string. So I'm just going to measure the length of the whole thing from here to here, and that comes out to 1.7 meters. Now, last thing we'll calculate real quick is the speed of this particular type of wave. Once again, that's going to be frequency times wavelength. So 10.4 hertz times 1.7 meters, and that should be about 18-ish meters per second, I think. Just shy of 18. About 17.7 meters per second. That's the speed that the energy is traveling from the speaker to the other end and then back. And that should be true for every wave of this type moving through this string. To prove that, I am now going to change the frequency that this thing is generating. I'm going to scroll up from 20.4 to 20.8. So the frequency has changed. And now if you look at the wave, we've got 4 antinodes and 5 nodes. We've got 4 of these points of maximum extension. So I've changed the wave frequency, and that has affected the wavelength of the waves traveling through this particular rope. We're now going to remeasure all of these things to see what's changed and see what hasn't. So I'll take this data over here. So this is the new information after we changed the frequency. So we'll remeasure amplitude, wavelength, frequency, and velocity. We'll go ahead and show again. I've doubled the frequency to 20.8. We've already got that number. Next, we'll remeasure amplitude and wavelength. For amplitude, going again from one of the nodes up to the maximum extension. That looks to have changed to about 20 centimeters. So the amplitude actually went down. 20 millimeters, excuse me. So the amplitude dropped, interestingly. It's likely that the energy of the wave is more spread out. And lastly, let's get the new wavelength. Now note, this isn't one full wavelength anymore, because now we've got 4 antinodes. This is now 2 full wavelengths, because we're going rest, up, down, rest, and then again, up, down, rest. So this is 2 wavelengths. So 1 wavelength would now be half the length of this rope. We could just cut the previous measurement in half, but I'll just show again real quick. From the end to the middle is now situated at it's a little longer than I would have liked actually. 900 millimeters, excuse me. 900 millimeters. Which is 0.9 meters. And now let's recalculate wave speed. So frequency times wavelength, but those two numbers have changed. And it might not be an exact match, but it's pretty dang close. Odds are I mismeasured the wavelength the first time. So note, we doubled the frequency. This cut the wavelength in half, but the wave speed is technically functionally unchanged. Actually, I'm going to go back and remeasure my original wavelength to make sure. So my setup needs refined and tuned. But note again, frequency doubled, the wave speed should remain the same. It didn't budge that much. So technically, functionally, the correct answer is wave speed remained constant even as the frequencies and wavelengths changed. What time is it? My computer's dead. 12:14. Thank you guys. So, and this happens because it's the same type of wave moving through the same rope. Every type of wave will have the same speed through the same medium. This is why what happens if you change the frequency is just that the wavelength will change to match in order to create the same velocity. And so different frequencies of sound all have different corresponding wavelengths in order to create the same speed of sound that you're used to. This means that very low frequency sounds would have very big wavelengths, and very high frequency sounds have very small wavelengths. Same is true for light, actually, because light is also a wave. Low frequency light has bigger wavelengths. High frequency light has smaller wavelengths. Red is the biggest wavelength, lowest frequency color, and violet is the biggest frequency, lowest wavelength color. And all the other parts of Roy G. Biv just are sandwiched in the middle there. The only way to change the speed of a wave is to change the medium it is traveling through, which means you could change the medium entirely. For example, again, speed of sound, air at 25 Celsius and 1 atmosphere of pressure is 343 meters per second. The speed of sound in water is typically considered to be about 1,500 meters per second. Same type of wave, but very different medium, so very different speed of sound. And what that means is that the same frequency of sound will have a different wavelength in the water than in air. Also, because the speed is just physically different, the sound travels faster. And that's actually why there's more echolocating creatures that live in the ocean than live on land. It's easier to rely on echolocation if the sound travels faster and travels further. On land, we really only have bats that echolocate, to my knowledge, but in the water, you've got literally every aquatic mammal, and maybe some fish. And then, I roughly remember from before my laptop died, speed of sound in Earth, like the physical ground beneath you, is even faster. So change mediums again and you get an even different speed for sound. So this means that Sound is faster in water than in air and faster still through the ground. So burrowing animals are even probably more sensitive to earth vibrations, which is good if you want to find food and avoid hunters. This is also where that trick that you may have seen in a movie or two where you stick your ear to the ground comes from. Because if someone's like trying to find a stampede or see if a train is coming, they might stick their ear to the ground. And this works because the vibrations from the stampede or the train travel through the ground to your ear faster than through the air. And that means they also come in clearer as well. They lose energy. Sound waves lose energy pretty fast because they're so slow in comparison to through the earth. So that's where that trick comes from if you've seen it in media before. It's also why earthquakes are dangerous, because the waves just travel too dang fast. So if you change the medium, you change the wave speed. And that's not just changing the type of medium, changing anything about the medium changes the speed of the wave. For example, I mentioned this number is the speed of sound at 25 Celsius and at 1 atmosphere. If you change the temperature to be at freezing, it drops to 331 meters per second, and at boiling, it goes up to 386 meters per second. So just changing the properties of the same medium affects the speed that the sound travels through it. As it relates to this machine, the primary property of the string that I can manipulate is its tension. And so right now this string is tied to this mass, and if I physically pull out on this mass, that's going to change the tension in the rope, and I can change it until we go from a 2 antinode sine wave, standing wave, to a 1 antinode sine wave, standing wave, excuse me. I change the tension in the string, and that's going to change the wave speed, which means that the same frequency now has a different wavelength than it did when the tension was less. Originally, the 10.4 gave us a 1.7 meter wavelength wave, but now this is only half of a wavelength. So the same frequency as over there now has a different wavelength because I changed the wave speed by changing the tension. And that's going to be one of the things you're doing in lab. You're going to have the same setup, manipulating the tension, figuring out what frequencies create what size waves at those different tensions. I'll point out as one last example, this is the principle that goes into violin, guitar, and piano strings. I'm not a musician, but I know that those instruments have strings and that all of those strings are tuned to different tension levels, correct? Those different tensions in the different strings cause each string to have a different wave speed, meaning it gives off a different frequency of sound for the same length of string. And so that's why those instruments have to be very finely tuned. Every single string has to be at just the right tension so that that length of string creates the right frequency of sound. And that's because when you change the tension, you change the wave speed. Change the wave speed, you'll change the corresponding frequency to wavelength, or change the wavelength for a frequency. So, the only way to change a wave speed is to change the properties of the medium it is traveling through. Questions? All right. Bring any and all these notes to lab whenever you have that this week. And let me know if you need anything, have any questions. Have a wonderful day.
Can I come to lab on?
Yes.